Good day. This is Engineer John Richard V. Maghina, and I will be presenting to you my research entitled Utilization of Waste Low Density Polyethylene Bag as Stabilizing Material for A-1-A Road Subgrade Soil. This research was conducted last 2017 as a partial fulfillment on my degree on Master of Science in Civil Engineering. Polymers are being utilized on a wide range of environments because of its durability and resistance to mechanical stresses. In engineering, plastic has been used as an additive to construction materials like concrete hollow blocks, concrete mixes, and bituminous mixes. The addition of plastic to these materials resulted to the improvement of material strength, durability, and quality. Soils, particularly in the Philippines, are weak and most likely to require additional effort in stabilization to comply with the standards and specification. On the country's national roads, pavement-related problems are due to subgrade failure. Subgrade is considered the part of the pavement system that is the layer of the natural soil upon which pavement and aggregate subbase is situated. It generally aids support to the upper layer of the pavement system. The performance of the pavement system greatly depends on the construction of the under materials such as subgrade, subbase, and base. Due to this reason, several soil stabilization techniques were introduced, such as the use of geosynthetics. Geosynthetic is a material that resembles fiber, which is made from polymers such as polyester, polypropylene, polyethylene, nylon, polyvinyl chloride or PVC, chlorinated polyethylene, and others. The five major geosynthetics used in practice are geotextile, geomembranes, geogrids, geonet, and geocomposite. There are four methods of ways how to stabilize the subgrades such as mechanical stabilization, cementitious stabilization, asphalt stabilization, and the non-traditional additive stabilization. Each stabilization method intends to improve subgrade strength and plasticity, aggregate interlock, reduce pore connectivity and air void content, and consequently susceptibility to moisture ingress. Several geosynthetics includes the addition of coconut fiber with tensile property which generally helps soil to prevent shear failure. In addition, cementitious-like product waste such as furnace slag and fly ash were also used to stabilize weak soil and to assuage its deteriorative effect to the environment. To assess Philippines' problem concerning both plastic waste and weak subgrade, plastic waste were added to the subgrade to improve its condition. At certain composition and minimal material processing, it can improve both strength and physical properties of soil. The strength properties of soil, which is the most important aspect in stabilization, pertains to its capability to carry imposed load. In subgrade, the bearing capacity is generally correlated with the values obtained from the California bearing ratio test. The main objective of this research is to assess the capability of plastic waste bag to stabilize soil and develop the percent plastic on subgrade equation in determining the resulting bearing capacity in terms of CVR value when specific amount of plastic is added to road subgrade soil. Specifically, the study will address the following: test the ability of plastic to stabilize soil by conducting a series of soil tests, examine the effect of reinforcing waste plastic bag on A-1-A soil type road subgrade soil, assess the significant changes in strength properties of road subgrade soil upon introducing plastic as stabilizing material, assess the ability of plastic to increase the bearing capacity and to decrease compressibility and permeability of road subgrade soil, and lastly is to verify the effect of plastic as stabilizing material if it conforms with the specifications and standards of the Department of Public Works on Highways on road construction. To carry out the objectives of the study, here is the conceptual framework of the research. Basically, there are six phases that we will use in this study. Phase 1 is the identification of plastic and road subgrade properties. Phase 2, the preparation of controlled samples. Phase 3, the preparation of the experimental samples. Phase 4, the laboratory testing. Phase 5, the data analysis and validation. And lastly, Phase 6 is the formula validation. So let us start at Phase 1, which is the identification of plastic and soil subgrade properties. Phase 1 generally is composed of 5 stages, with its first stage as review plastic waste components and properties. So based from the thorough review of the related literature, there are 6 types of plastic that is being used and utilized nowadays. For the second stage is to identify plastic waste purpose on road construction. Based from the related literatures, the purpose of plastic in road construction are as an additive to bituminous mix. It is also an additive to concrete mix. It is also used as slope protection, and it is also used for ground improvements for foundation. The third stage is to enumerate the properties of soil subgrade. So generally, the properties of soil subgrade is divided into two, which is the physical properties and the strength properties, with the physical properties as the water content, densities, plastic limit, liquid limit, shrinkage limit, liquidity index, plasticity index, the maximum dry density and the optimum moisture content. On the strength properties, it is the bearing capacity, the shear strength, the consolidation, the lateral earth pressure, the slope stability, and the permeability and slippage. For step 4, identify the standard testing procedure for soil. So the standard testing procedure for soil is generally depends on the AASHTO designation or the standard testing procedure of the AASHTO. As shown on the screen, here are the following AASHTO testing procedure that needs to be followed in order for us to obtain each properties. And the fifth stage, or the last stage of phase 1, is to identify the existing standard and specification for road construction. So the table shows the specification or the requirements mandated by the Department of Public Works and Highways. Phase 2 is the preparation of controlled samples. Generally, Phase 2 is composed of 3 stages, namely, the first stage is obtaining soil sample from the site. So soil sample from the sites were taken from the 3 main road projects of the Department of Public Works and Highways, namely, for 17 CD64, concreting of access road leading to PNP resettlement and housing project San Miguel, Bulacan, the rehabilitation and reconstruction upgrading of damaged paved National Road San Miguel, Cebu, and lastly is the rehabilitation, reconstruction, upgrading of damaged paved National Road including drainage in Sibol Biak na Bato, San Miguel, Bulacan. For the step 6, perform Atterberg limit test. So the Atterberg limit test aims to determine the Atterberg limit, which is generally includes the liquid limit, plastic limit, and the plasticity index. So the 8th stage of the phase 2 is the performance of sieve analysis to classify the soil. According to the sieve analysis, Site 1 soil classification is A-1-A, Site 2 soil classification is also A-1-A, and Site 3 classification is also A-1-A, which generally sees or say that the soil in San Miguel are most likely composed of a A-1-A soil type. The phase 3 of the research is the preparation of experimental samples. So phase 3 consists of only one stage, which is the addition of specific amount of plastic waste in the soil mixture. So generally, specific amount of plastic will be added to the soil. The plastic size to be added is 10 by 30 millimeters, and the amount to be added ranges from 0.1 to 1% by weight of the soil. The fourth phase of the study is the laboratory testing. The phase is composed of 2 stages, which is the first is to perform the Proctor test. Proctor test generally aims to determine the maximum dry density of soil. So table 3.9 shows the maximum dry density of soil with different amount of plastic waste. Trial 1, which generally shows the maximum dry densities of soil with having plastic obtained from site 1, trial 2 for site 2, and trial 3 for site 3. The graph shows the maximum dry density versus the percent plastic weight of soil. So as we can see, adding plastic generally improves the maximum dry density of soil, having its maximum efficiency as 0.5% plastic. Another property that we could determine in Proctor test is the optimum moisture content. So the table shows the optimum moisture content of reinforced soil sample with different amount of plastic. So here is the graph showing the optimum moisture content and the percent weight of plastic added on subgrade soil. As we could see, adding more plastic exhibits into a lower moisture content, which generally an indication that the soil is being improved. The maximum improvement of the optimum moisture content can be seen at 0.5% plastic composition on road subgrade soil. The second step in the laboratory testing is the performance of the California bearing ratio test. So the table shows the California bearing ratio test obtained from the soil sample with different amount of plastic. As we could see on the table, the addition of plastic weight on soil generally improve its CBR values. The fifth phase of the study is the data analysis and validation. The data analysis and validation phase is composed of 3 stages, having the first stage as to generate graphs on Excel and analyze the results using t-test. So we have the null hypothesis as the addition of plastic waste to soil subgrade do not increase the bearing capacity and does not decrease compressibility and permeability of road subgrade. And its alternative hypothesis is plastic reinforcement on stabilizes soil by increasing its CBR values. First, we get the experimental mean by adding all the CBR values obtained from the soil sample having plastic composition. And based from the computation, the experimental mean is 50.69. For the hypothesized mean, we simply get the average of the CBR values of the controlled sample, and we obtain the hypothesized mean to be 30.42. We then use the formula displayed in the screen to get the value of t and perform t-test with the degrees of freedom of 2. Based from the one sample t-test performed on CBR values, we could see that the t-value is 13.32, which is in the rejection period. Hence, we reject the null hypothesis and conclude that plastic reinforcement stabilizes soil by increasing its CBR value. The second stage on phase 5 is to perform a polynomial regression analysis in Minitab to generate the regression equation or the percent plastic on subgrade equation. Table 3.14 shows the CBR values with its corresponding amount of plastic on road subgrade soil. In polynomial regression, it is very necessary to identify the best fitting curve in the graph. And based from the Minitab analysis, the best fitting curve is found at the 6th degree curve, having the equation as seen in the screen. So the equation describes the relationship of CBR and the percent plastic on soil subgrade. This equation is now then called the PPS equation. The fifth stage in the data analysis validation phase is to determine the compliance with the DPWH and ASTO specification in road subgrade construction. Basically, the minimum requirement for CBR values is 30%, and we could see that the control sample failed to meet the specification, and upon the addition of plastic on road subgrade, the CBR values increases and therefore pass the specifications. The final phase of the study is the formula validation. The formula validation phase is composed of a single stage which aim to validate the accuracy of the PPS equation using t-test. In order to do this, we perform 7 California bearing ratio tests on soil sample with random percent amount of plastic. The mean CBR that we obtain is 52.30, will be considered as the experimental CBR values. On the other hand, we use the PPS equation to identify the predicted CBR values of soil samples with different amount of plastic. And based from the calculation, we obtained a mean of 52.54 CBR value. T-test is then used to validate the accuracy of the PPS equation. We set the null hypothesis as the PPS equation is a tool in predicting the bearing capacity of plastic reinforced subgrade soil, while the alternative hypothesis is the PPS equation is not significant in determining the bearing capacity of the plastic waste reinforced soil. Based from the Minitab analysis of one sample t-test, the t-value is t.07, which is inside the non-shaded part of the normal distribution curve. Hence, the null hypothesis was not rejected, and our conclusion is percent plastic on subgrade equation is a powerful tool in predicting the bearing capacity of plastic reinforced subgrade soil. For the conclusion, the research conducted series of laboratory tests such as Atterberg limit tests in order for us to classify the type of soil used in the study. In the moisture density relation test or the Proctor test, the addition of plastic on soil improved the maximum dry density and the optimum moisture content by increasing and decreasing its values respectively. At 0.5% plastic by weight of soil, the maximum improvement on MDD and OMC were attained. Subsequently, California bearing ratio test was conducted on several soil samples containing different amount of plastic. The addition of plastic bag waste on A-1-A type of soil increased the CBR values. An increase in CBR value was evident on soil having amounts of 0.1% to 0.5% plastic by weight of soil, and beyond this amount, the CBR value began to decrease. From the t-test, the plastic reinforcement significantly improved the quality of soil by increasing its CBR values. Hence, there was an increase in the bearing capacity of subgrade soil as well as decrease in both compressibility and permeability. Improvement by reinforcing waste plastic on soil passed the standard specification mandated by the Department of Public Works and Highway, and it conformed with the requirement of the American Association of State Highway Officials or the AASHTO. The study was able to develop the percent plastic on subgrade equation using a polynomial regression in Minitab 18, and it was verified that the equation is accurate in predicting the resulting CBR values when specific amount of plastic is added on soil. For recommendation, expanding the area of the study by obtaining soil subgrade samples on the different barangays in San Miguel, Bulacan. It is recommended to consider more amount and increment of plastic waste reinforcement in soil subgrade sample. It is good to perform CBR testing and more trials to improve the accuracy and precision of the mathematical model obtained from the polynomial regression. It is highly recommended to observe the effect of plastic waste bag upon the addition on road subgrade soil of other physical properties such as Atterberg limit, void ratio, and specific gravity. It is also good to consider and observe the changes in other strength properties of soil such as shear strength, angle of internal friction, lateral earth pressure, and seepage. It is highly recommended to consider variation in the type of plastic waste to be used. Consider plastic bottles, PVCs, and other type of polymers as reinforcement in soil subgrade. It is highly recommended to conduct testing on the other type of soil subgrade. It is highly recommended to study the effect of reinforcing plastic on weak, clayey, and subgrade soil. It is also recommended to use another statistical method in validating the formula in data. Consider t-test for a larger scale sample. The analysis of variance or ANOVA could be used to compare the means of the independent variable, which is the percent plastic, and the dependent variable, which is the California bearing ratio. It is highly recommended to perform other laboratory testing procedure on the reinforced soil, such as direct shear test, triaxial compression test, and confined compression test, vane shear test that would made to assess the changes in strength properties of soil samples. It is also good to consider other international testing procedure aside from what is indicated in AASHTO. Procedure from ASTM could be adopted as an additional source of data for a more valid result. And lastly, it is recommended that the application of plastic waste as reinforcement for soil must be tested on the actual site. Conduction of the field density test of the FDT would be a great source of another data which can be correlated with the waste plastic ability to increase the actual maximum dry density of soil. So this ends my presentation. Thank you so much for listening, and I hope you gained something on my research.